Alright everybody, this is Dr. Pennington, going to be talking today about ionization energy and electron affinity. This follows on a little bit from our discussion of electron configurations. We're going to focus a lot more on ionization energy than we will on electron affinity, but I will cover both. But the emphasis is definitely going to be on ionization energy, simply because the trends are easier to follow. Alright. Ionization energy, broadly defined as the energy required to remove an electron from an atom. Usually an atom in the gaseous state, but I'm not too concerned about whether you put that down or not. The important thing is that you understand, in writing out the ionization energy for something, what we're really talking about is this. The energy required to do this, to pull an electron out of sodium that originally had a 0 charge, that in the end has a +1 charge because it lost a negatively charged electron. Now this is pulling an electron out of something. Now pulling something out of something else always requires the input of energy. This ionization energy is always endothermic. In other words, it's got a positive delta H, it requires energy. The big question across the periodic table is how endothermic is each element? Turns out that different elements require different amounts of energy. Some groups have elements that require less energy to do so, and some have more. And you can actually figure it out just by looking at the two things, the element's size and its group, or number of valence electrons really. So for example, to remove an electron from sodium, the ionization energy is IE sub 1, meaning first ionization energy, is 496 kilojoules per mole. Now you guys don't need to worry about that number other than the magnitude of it. I'm not going to have you guys have to memorize anything like that. You can also talk about the second ionization energy. And for sodium, that energy goes way up. Notice the IE2 is almost 10 times the IE1. So to remove the first energy, to remove the first electron requires this energy. To remove the second requires much more. And here is why. The electron configuration of sodium has 11 electrons. 1s2, 2s2, 2p6, 3s1. That's the orbital with the outermost electron in it. It's all by itself. That's sodium. Sodium really wants to obtain this electron configuration by losing the outer electron, and so that's why losing that is not very difficult. Its ionization energy in the grand scheme of things is actually quite low. But think about it, what would have to happen for us to go to Na2+? We'd have to lose another electron and go to an electron configuration that looks something like this. Now how likely do you think this would be? How stable do you think that is? We know that this is perfectly stable. This is the electron configuration of neon. How likely is this? Well, what's the likelihood of pulling an electron out of a noble gas? Of course it's not going to happen. So the less likely it is to happen, the higher amount of energy is required to do it, because you can always force it to happen, but it requires a lot of energy. That's why Na2+ is not something that you're going to see. If we were to look at, say, magnesium, for example, alright, magnesium has an electron configuration of 1s2, 2s2, 2p6, 3s2. This s orbital here is full. So removing one electron to go to Mg+, in other words, an electron configuration that looks like this, well, that's going to be much higher here for magnesium than it is for sodium. Simply because losing this one electron is highly likely, because you go down to the next full orbital. Here you don't. Now going from here down to this, I hope you can see, is actually much more likely for magnesium. There is a reason why magnesium forms Mg2+ and does not form Mg+. Alright. So the the ionization energy you can actually look at in terms of magnitude based on the group in the position in the periodic table. We're going to focus actually primarily on first ionization energy. So for example, this right here. or this right here. And you'll see there is a trend. For sodium to magnesium, the ionization energy for magnesium for the first ionization energy is higher. And that trend actually repeats itself across the whole of the periodic table. For sodium, it's very easy to remove that outer electron. For magnesium, it's less easy. You've got to have more energy. More energy for aluminium, more for silicon, more for phosphorus, more for sulfur, more for chlorine, and even more for argon. Because argon has 8 outer electrons, it doesn't want to have any removed. Chlorine's got 7, it wants to gain 1 more. It certainly doesn't want you taking any away from it. So the first ionization energy has a very particular trend. It increases going left to right. But let's also look at ionization energy going down a group. Doesn't matter which group you're looking at, the trend is the same. Look at lithium. Or actually, let's start sodium. 2s1. Sorry, sodium's 3s1. Potassium is 4s1. Rubidium is 5s1. Cesium is 6s1. Francium would be 7s1. Lithium would be 2s1. They all have the same number of outer electrons. You know that from looking at the periodic table and looking at the group. But which one's easiest to remove? Well, it's the one that's furthest away from the nucleus. When we did the demonstration in class about potassium reacting more violently with water, it's very simply because the outer electron in potassium is much easier to remove when it reacts with water, so it gives out a lot more energy. There's a reason we didn't do it for rubidium, because I don't want to blow us all up. Not today, anyway. No, seriously, I just don't want to blow us all up. And there'd be much more likelihood of that happening with rubidium and cesium, because the outer electron is that much easier to remove. So the ionization energy, first ionization energy, increases going left to right and decreases going top to bottom. So francium has a much lower ionization energy than, say, sodium, hence it would be a much more vigorous reaction. And we can use this trend to allow us to compare any two elements and see which has the higher or lower ionization energy. So we're going to look at these two, and I'm going to ask us, tin or iodine, which has the higher first ionization energy? Well, let's compare them in the periodic table. There's iodine, there's tin. Ionization energy increases left to right, therefore iodine is going to have a higher first ionization energy than tin. Calcium and strontium, well, there's calcium, there is strontium. They're in the same group. Ionization energy decreases down a group, so therefore strontium should have a lower first ionization energy than calcium. Alright? Strontium is lower than calcium, and that's actually true. Now, when we look at carbon and phosphorus, it's a bit more complicated because carbon and phosphorus are neither in the same period nor the same group. So we've got to be a little bit careful about this, alright? And in some cases we cannot definitively give an answer. So let me just show you what I mean by that. We know left to right ionization energy increases, so based on that, phosphorus should be bigger than carbon. But we also know going down a group, in general going down, ionization energy decreases. So in that way, phosphorus should be less than carbon. So notice here we have two opposing effects. And unless we have extra information, we don't know which is the more important one. And so therefore, we would need more info because the two effects oppose each other. But when we look at fluorine and sulfur, let's just find their positions again. Alright, so fluorine is here, sulfur is here. Again, fluorine and sulfur are not in the same period or group, but left to right, we know ionization energy increases. So according to the left to right rule, fluorine should have a higher ionization energy than sulfur. Top to bottom, sulfur is lower than fluorine, so therefore sulfur should be less than fluorine. And now notice these two are actually telling us the same thing, that fluorine's higher than sulfur in both cases. So therefore Fluorine's higher than sulfur. So therefore iodine is higher, calcium is higher. Can't say anything here, fluorine is higher. So you can compare ionization energies of any two elements without much of a problem. Now what if we were to do this? If we were asked to arrange the following elements in the increasing order of first ionization energy. Increasing means we've got to put the lowest first and the highest last. And we have 5 elements. Actually, that should be sulfur, lithium, selenium, chlorine, calcium. You can usually estimate that if we have any elements in groups 1 or 2, they are more likely to have lower first ionization energies than anything that's over in the other groups. So for example, anything over here in these first 2 groups is more than likely to be lower than anything over here because of this rule right here. Alright. So we can say that based on that, what do we have? We have lithium that's in group 1 and calcium that's in group 2. Sulfur, selenium and chlorine are all in groups 6 and 7. So we're going to look at these 2 first, lithium and calcium. Here's lithium. Here is calcium. Alright? It's pretty much a guarantee that group 1 is going to trump group 2 in terms of low ionization energy because of the outer electrons. So what that means is lithium, because it's a group 1 metal, is going to have the lowest ionization energy. Calcium, because it's the only element in group 2, although it's higher than lithium, it's going to be lower than everything else. And we've got to look at the other 3 to compare them. The other 3 were, there was chlorine, there was sulfur, and there was selenium. Alright? So we know that sulfur and chlorine's going to be higher than sulfur. But we also know, so we know that chlorine is going to be higher than sulfur. But we also know that selenium is going to be lower than sulfur. And if selenium is lower than sulfur, then selenium's got to be lower than chlorine. Meaning, out of these 3, chlorine's got to be the highest, selenium's got to be the lowest. Alright, and we can add that to the rest of our numbers here and say if out of those 3 selenium is the lowest, then we have sulfur, then we have chlorine. And if we were to actually look up in the textbook and find the kilojoules per mole of each of these, we'd find that what we just said is absolutely true. Lithium has a first ionization energy of 520 kilojoules per mole. Calcium is 590. Selenium is 941. There's a big jump here because we jumped from group 2 to group 6, so not really a surprise. Sulfur is 1000. And chlorine is 1251, again a big jump because we go from group 6 to group 7. That is ionization energy. So we're just going to focus a little bit on electron affinity here and then we'll be done. Alright? Electron affinity is kind of the opposite to ionization energy. If ionization energy is the amount of energy required to pull an electron out, electron affinity is the energy involved in sticking an electron in. Alright? And when we go back to the periodic table here, and we ask ourselves, based on these electron configurations, which group of elements, group 1, 2, 3, 4, 5, 6, 7, or 8, do you think has the elements in it that are most happy to accept electrons, to accept 1 electron? Well, it'd be group 7, because those have 7 electrons. They want 1 more. What's the likelihood of group 1 wanting electrons shoved into them? Well, not very high at all. Group 8 is not very high either. The problem with electron affinity is a much more complex issue than what I'm just saying, so you can't easily talk about trends the way you can with ionization energy, and hence we're not going to focus on it too much. But we can talk about some things. Usually, for example, chlorine accepting an electron to make chloride. This is very stable, this is not. It would make sense that that's kind of a favorable process. Its exothermic energy is given out. Now, one other problem with electron affinity is not every one of these is exothermic. Some are endothermic. Some have numbers that don't quite follow any sort of a trend. But the general, and this is general with a capital G, the general trend for electron affinity is that increases. So electron affinity increases or becomes, what that means is becomes more exothermic going left to right across the periodic table. And that's only a general trend because there's lots of exceptions. Alright? So, for example, chlorine plus an electron going to chloride is much more likely than sodium plus an electron going to sodium minus. Alright? Although this can actually occur, it has a much lower, much less exothermic value associated with it. Meaning, for chlorine it's much more likely than for sodium. That's for chlorine, that's for sodium. So as we said, it increases, becomes more exothermic going left to right. The only other thing to understand, although electron affinity and ionization energy look to be the opposite, they're in fact not. They're different. There are many exceptions to this trend. We're not going to focus on those. Ionization energy is the take-home message here. So if you understand ionization energy and the trends, more so than they do for electron affinity, that will be good. Alright, thank you.